Hi everyone. Today I'll present for the STACS conference the article Tight Approximation Guarantees for Concave Coverage Problems, which is a joint work by Siddharth, Barman, Omar, Fawzi, and myself, Paul Fermé. And so we'll look at coverage problem, and especially the maximum coverage problem. This is a well-known variant of set cover, which is the following. You've got some elements and some cover sets, and the goal is to maximize the coverage, so the number of elements covered by taking only k cover sets. For instance, here if you just take 3 cover sets, the best one can get is just 9 elements, taking, for instance, those 3 1. So this problem was well studied. It's been shown that it's NPR to do a better approximation ratio than 1 minus e minus 1. Since C is sum-modular, the natural greedy algorithm, which just takes cover sets by cover sets by taking the one that makes the value the greatest at each step, achieves this approximation ratio in polynomial time, and so the problem complexity is closed. The question we ask now is, what would happen if we take into account elements that are covered several times? In fact, this is motivated by some kind of applications one can think. For instance, network coverage, you've got some antenna placements which are represented by these cover sets, and you want to place k antennas in order to maximize the coverage among all agents which need this network, and also the bandwidth. So you've got some kind of trade-off to do between the fact that cover everyone and that if more people are covered by a small number of antennas and even covered twice, this will be better. Also, you can think of a democracy motivation, which is multi-winner elections. So here, the context is quite different. Each cover set corresponds to a candidate, and the elements covered are the people who have voted for this candidate. In this setting, voters can vote for several candidates, and the goal is to find k candidates that represent the best the population. And so for this, you want to take into account that you cover most people, but also the fact that if more persons have voted for some particular candidates, they must have more chance to be chosen. So both and other of these applications can be studied in that way. We call that the utility of element covered C times will be given by some function of C, phi of C. And so we will ask some properties about this function. So it has to be non-decreasing because we want the utility to increase when you're covered several times. And it will be concave because we want the marginal gain to decrease. And okay, small normalization assumption. And what kind of things do we get with this? Okay, so the function that we maximize now is C phi of S, which is defined like this. So the sum of phi of S not A, which is the number of times A is covered by S. And still, S has to be of size K. For instance, a function phi is the following: it's 0 in 0, 1 in 1, and then it's concave non-decreasing. So one example one can look at is simply to take the minimum of phi of x is the minimum of x and 1. So meaning that if you're covered more than once, you count for 1. And as I said, as I say, this is exactly the maximum coverage problem we'll recover here. And we get the same best solution here. But for instance, you can do something quite the opposite direction, which is just to take phi of x to be the identity. And then the solution is quite easy to find. You just take the k biggest set. And for instance, here, the optimal solution is the following. So D is covered twice, E and B are covered 3 times. And so the global value is 12. But you can think also of intermediate situation. For instance, if phi of x is the minimum of x and 2. So you count up to 2, and then you don't give any advantage. So this is a solution, and the choice of phi depends on the actual problem you're looking at. And for that situation, you get another solution, which is given like that. And here we get that the best value is 11. So the problem we look at in the end is the following. We just add, compared to the previous examples, some positive weight depending on the element. So you just have an element which has a weight. We still ask a phi non-decreasing concave. And with this assumption, we get that there exists a polynomial time algorithm which achieves some ratio. We have to call the Poisson concavity ratio of phi. And for phi sublinear, we've shown that it's in fact tight under P different from NP. And so what is this ratio? You take the minimum of all this kind of ratio alpha phi of x, which is the expectancy of phi of Poisson of x divided by phi of the expectancy of Poisson of x. And since phi is concave by Jensen's inequality, one can already see that this is indeed between 0 and 1. Okay. So what was done before? As I've said, the C of phi is submodular, and for submodular maximization problem we look at, there is a generic algorithm by Svianico et al., which gives a ratio depending on the curvature C, and gives 1 minus C E minus 1. And we've shown that alpha phi is better than this, and in fact, in most cases, it's strictly better for this particular case we look at. And the idea behind this is kind of that the curvature is a kind of worst case curvature, whereas our concavity ratio is kind of an average one. So this is kind of the idea. And so there was another problem which was studied, which was called the L multi-coverage problem by Barman for the et al. And here it corresponds to phi of j equals to min of j and L. So we've seen a bit of those examples. So you've got this ratio, and it was shown to be tight under the unique games conjecture. And for us, one can show that, in fact, alpha phi takes its minimum in L, and where its value is exactly this. And so we've shown a stronger result, so that it's tight under P, different from NP. And the closest result from us is the result which was shown for geometrically dominant phi. And in that setting, you get the ratio expectancy of phi of Poisson of 1. And this was shown that it was tight under the same assumptions. So we've shown that if we add indeed these further constraints that phi is geometrically dominant in our context, we have indeed that our coefficient alpha phi takes its minimum in 1, and so that it's equal to these results. And this means that it is indeed a particular case of our result. One should note that these results didn't, for instance, cover the L multi-coverage problem, since the minimum is taken in L in that setting. And also, we have much more other examples where these do not apply. For instance, let's look at this table. So we've got summarized some of a particular case of our problem. So the maximum coverage, the L multi-coverage. And next, this is called the PAV. It's the proportional approval voting, which is something which is used in this multi-winner election context. And one can think about capping this. So you just take some kind of function, and then you choose a rate, for instance, 3, and then it's it remains constant. All of those functions which are capped were not covered by the geometrically dominant setting. And for us, we've shown some new results about those. And for instance, for the proportional operating capped at 3, we get this ratio. And then the same for the same reason, we get this result for the vehicle target assignment problem. So this is just this function, and we'll see it has some applications in game theory and military applications. And so here you see that when it's capped at 5, the minimum is taken at 5. And so in particular, it means that it was not covered by the geometrically dominant setting. So, okay, now let's look at how we prove the positive side of this theorem. So mainly how the algorithm works. So it's a common idea. It's a relax and round strategy to achieve this ratio. So it's not combinatorial. So first we relax our problem. Okay, so for this, we need first to consider the piecewise linear extension of phi on R plus, because it was only defined on integers yet. And we just define this linear program, this program. And one can see that if you just ask xi, the xi's to be integers instead of between 0 and 1, one recovers, in fact, the phi max coverage problem. For now, it's not clear it's indeed a linear program because we've got this constraint, which is not linear. But in fact, this can be coded by m linear constraints with phi j linear interpolation of this. And thanks to concavity of phi, this will be linear and works. So a picture is better than a long speech. So it's just because of this. You've got some concave non-increasing function. You want to encode the fact that it's smaller than phi. So you just put all of these linear constraints at the same time. And when you satisfy all of the red constraints, you have exactly what you want. And since phi is piecewise linear, it's exactly its piecewise linear extension this way. Okay. So the second step is to round. And for this, we'll use a technique which has shown its strength, which calls the pipette rounding. So this is the first step. So I recall how it works. Given some function f defined on sets of size m, at most m, you can see this as a small function f whose input is m integers between m bits. This codes set. And so the multilinear extension f, so any real number between 0 and 1 times m, is given as this f of x1 up to xm. You take the expectancy of small f of x1 xm where they follow independent Bernoulli rules. So the thing is, with this multilinear extension, one can find with the pipette rounding procedure, as soon as this function f is computable in polynomial time, you can get an integer solution from a fractional solution in polynomial time. And this will satisfy this inequality. So this is the main pipette rounding theorem. And so in our setting, so let's call x star an optimal fractional solution. This means that C phi of x int indeed is larger than the expectancy of this. Indeed, when f is chosen to be, when f is taken and big F, the multilinear extension is taken on integer points, it's equal to small f. And here we've taken C phi to be small f. So we got this first inequality. So we've got an integer solution, and here is the optimal solution of our relaxation. And we want to bound this quantity. So this is the main theorem. We show that we have this, meaning that the expectancy of this quantity can be lower bound by this minimum of alpha phi of j times the objective value. And okay, this implies that we get a polynomial time algorithm. Indeed, we've got C phi of xn. So thanks to pi-page rounding, it's bigger than this. Thanks to this approximation guarantee theorem, it's bigger than this. And since this is the optimal solution of the relaxation, in particular, it's greater than the maximum over integer choices. And so this sequence of inequalities gives us what we want. So I just point out the key tool of the approximation algorithm, which is the following. Mainly, here you've got an expectancy of C phi of x, and mainly it's a phi of some sum of Bernoulli. And here you've got something which is about Poisson law. And so the main tool is this kind of inequality. And this, between Bernoulli law and Poisson law, comes easily when use convex order. So this was found by Barman et al., and it applies again here. And this is the following. And one can show that it's true for Bernoulli and Poisson. And since it's a preserved full convolution, and you've got this Poisson law follows some nice additive law, we get the wanted convex order inequality, which gives this main inequality we need for our theorem. Okay, I won't go in more details, but this is the key idea to prove this approximation guarantee theorem. So now let's finish and look at some application. So we've seen the general problem of doing this, but there is also a small variant which is called resource allocation in multi-agent systems. Now you've got some resources, you've got k agents, and each of these agents has some particular personal resources. And the goal is to optimize this function. So it's quite the same. So the main difference is you've got k agents and each one has its own resources. In spite of having a full load of resources, you can spread as you like. And so, in fact, this can be shown to be some phi microcovariant distance under a partition matroid constraint. And in fact, we have a stronger version of our theorem which works for matroids constraints. So this will be a particular case of this. And we can adapt the hardness proof. I haven't mentioned it. And we get the same theorem and the same tightness here for this setting. In particular, there is something which is well studied. It's the case of the vehicle target assignment problem. So this has to military. You've got resources which corresponds to targets. So the elements are targets. The agents corresponds to vehicles. Each agent is a vehicle. And each vehicle has several possible assignments. He has several positions. And this means he targets he protects some targets. And you've got this function which is used to call the way you can protect a place. Or it's meaning that you can destroy more if there are more weapons there. Although this is more about placing persons for defense mainly. And okay, so this function is non-decreasing concave, phi of n equals small of n. So we get the tight ratio 1 minus e of minus p over p in the context of this resource allocation. And one can look also at the cap version of this problem. For instance, if you think of a threshold where you can consider that the targets are destroyed. And these are totally new coefficient we get. Indeed, okay, we've got this. So the 1, 2, 3, 4, 5 are the way it's capped, and the infinity one is the non-capped version. So the non-capped version was already shown on this vertical line is just the L multi-coverage, but all of these coefficients in between, and this one is just the maximum coverage standard. But all of these coefficients in between are new approximation ratio coming from our results. Okay, and so the main motivation of this game theory aspects of different agents and different resources is that you can think about game theory aspects of this. So the goal here, you want to bound the welfare loss due to self-interested choice of each agent. So mainly, each agent wants to maximize its own bit. And this stops when you get some Nash equilibrium. So meaning that at a position, if someone changes his choice, it only decreases the global value. And so the price of anarchy is the worst Nash equilibrium one can get, just by making local actions without communication with each other. So the idea is it's in name. And so in the setting of the 5 resource allocation problem, the value of the price of anarchy can be computed by linear programs. So this was the result by Pacanier and Marden. And this gives some, and the price of anarchy gives some approximation ratio for an algorithm. Indeed, in most settings, one can achieve this ratio in polynomial time, making in order to find some Nash equilibria. And so in particular, this implies that it's smaller than our approximation ratio because of the hardness result, meaning that you can beat this ratio in polynomial time. We know that the price of anarchy is always smaller than our ratio. And the question we want to ask is, so is this price of anarchy really bad or good? So is it tight with this approximation with the hardness result? Do we lose compared to the global approximation algorithm we've shown? And so there was an insight first that it could be the same. In particular, for the L multi-coverage, it was shown that in fact they are equal, these coefficients. But in the particular case of the vehicle target assignment, we've shown that this coefficient can in fact be strictly greater than the price of anarchy guarantee. And this is depicted as here. So in black, you've got the approximation ratio, and in blue, you've got the price of anarchy for 20 players, and this only decreases. And so there is a gap between those two curves. And as a comparison, we have just the standard curvature algorithm, which is a much worse guarantee. Okay, so to conclude, we presented here the phi max coverage problem, which is a generalization of the maximum coverage, where having C copies of an element gives the value phi of C. And we've shown that for non-increasing concave phi, we've got an approximation guarantee given by this Poisson concavity ratio, which is the minimum of the expectancy of phi of Poisson of x over phi of the expectancy of Poisson of x. And we've shown also that this is tight for some linear functions phi of n equals smaller of n. And this beats the generic algorithm, the best known, as soon as we've got that phi is not linear from 1. And in this case, they are in fact equal. So there are small open questions. So we presented a relax and run strategy. So does there exist some combinatorial algorithm that could achieve alpha of phi? So, and the second question is whether this hardness result remains true when phi is not sublinear. And so thank you for listening, and goodbye.